let's go. We are going to take homework questions first, if you have any, with respect to chain rule. You're all good. Okay, moving on. What's that?
No, I don't have a book, so I don't know
Here you go.
what I
I don't have a book either. Somebody grabbed my book. Oh, is that my book?
That was, I'll let it go.
Okay.
I don't have a book. What? Oh.
Okay, what happened? Yeah, I think there's just an algebraic simplification problem there. It's pretty clear that this has to be 2t squared and that has to be t squared, so that has to be negative, that has to be 3t squared to begin with. Yep. And I think all the rest follows from there. Okay, are there any other questions? If not, we're going to talk implicit differentiation. All right. So, this is a thorny kind of concept. Justin, would you mind hitting the door, please? This is a thorny kind of a concept because what we are going to do is to define a function implicitly by specifying a function of two variables which must equal to 0. So an example of this could be x squared plus y squared minus 16 is equal to 0. Or we could have something that's more prosaic, like x squared plus 2x plus 3 minus y is equal to 0. Or we could have something really exotic, like x cubed plus x plus y cubed is equal to 0, something like this. And all three of these are implicitly defined functions. But now, here's the weird part about this. The graph of each one of these is going to be the set of all points x, y that satisfy the equation. And when we graph the set of all points x, y that satisfy the equation, we don't always get functions. And in particular, when I take a look at this one, just a little bit of rearrangement puts it into a more standard form. Look at the standard form for this guy. Yeah, which is the equation of a with radius of no 4 and a center at. Okay, so here's our first one right here. X squared plus y squared is equal to 16, like so. And you can see that this is not a function. So what do I mean that it's an implicitly defined function? If I look globally, it is not a function. However, if I look locally at almost every point x, locally, I have y as a function of x. What do I mean by that? Almost every point. In fact, for this one, there are only 2 points that are exceptions. Y equals, let's call it g of x, some function of x. What do I mean by that? What I mean is pick a point, almost any point. Let's say right here. And there is a neighborhood around x equals c right here, such that in this little neighborhood, that little segment of the function, the subset of the graph, defines a legitimate function of y as a function of x. Does that make sense to everybody? In other words, there is a neighborhood of x0 or c, neighborhood of c, such that y equals g of x for all x in the neighborhood. And we can actually find that function by doing a little bit of algebraic solving. If I take the equation x squared plus y squared equals 16, and I ask simply, what is y as a function of x, then what I find is that there are two answers to the question. One answer to the question is y is equal to root 16 minus x squared. And the other answer to the question is y equals negative root 16 minus x squared. And each of these represent different branches of the curve x squared plus y squared equals 16. These are different branches. And the top branch is the top half of the circle. And the bottom branch is the bottom half of the circle. Just like that. Does that make sense to everybody conceptually, what we're talking about here? And so what I claim is that for almost every point, I can find a branch where y is a legitimate function of x. What do you think the only two exception points are? Yeah, right on the sides, right here and right here, if I take any neighborhood around x equals -4, I will find that both the top branch and the bottom branch are part of that neighborhood. And when I do a vertical line test, it fails. What is it about -4 and 4 that could have enabled us to predict that? Yes. They are points of non-differentiability. Very good. And in particular, what type of non-differentiability do we have there? Vertical tangents. That's exactly right. And so here, then, we're going to have a theorem, and that is if dy dx exists at x equals c, then there is a branch such that y equals x for x in the neighborhood of c. And I'm not going to prove this theorem. I think it requires more apparatus than we have just yet. But I'm going to appeal to its plausibility with just a graph. So here's our plausibility argument. And that is that if I have some weirdo implicitly defined curve like so, then, as long as dy dx exists, in other words, not here or here at the vertical tangents, if we are at some point like right here, then I can draw a little piece of curve right there that is going to pass the vertical line test, because since my derivative exists all throughout here, my curve is smooth, and it cannot come back over itself to fail the vertical line test without dy dx going through each other. Okay, now the question is, how do we actually find the dy dx here? And to do that, we are going to use the derivative operator. This is almost purely a skills class. So, if I have the relationship x squared plus y squared is equal to 16, then what this does is it defines a relationship between the set of points x, y, and that relationship is really interesting. It says for any point x, y on the curve, the x squared plus y squared has to be constant, has to be equal to 16. And so because of that, the rate of change with respect to x of each side must be equal. Because each side is equal, it must change at the same rate. And now what I can do is to walk through the derivative taking process on both sides, paying attention to the chain rule. Yes?
Sorry, do you have the definition for branch?
Good. That's right. So this was an undefined term back here. And a branch is going to be really the function y equals f of x. It is going to be a set of points on the curve y equals f of x such that the points x comma y, or the points x comma f of x, satisfy if I have the branch of the implicitly defined function capital F of x, y equals 0, it's going to be a function of x such that all the points satisfy F of x, y equals 0. In other words, they are points on the curve that give me legitimate functions. And for this curve, we would say there are two branches. One is here, and one of them is right here. And visually, I can identify them by the points of vertical tangency. Mathematically, they are identified by the fact that we pass the vertical line test for every point in the branch. Does that make sense? Yep. And when we get to differential equations, we're going to talk about branches, but we're going to impose an additional condition, and that is that these branches have to be smooth. They cannot have any points of non-differentiability whatsoever. Yes?
So then in the x squared plus y squared equals 16 on that. So one branch would be like, so the branch is y equals f of x, but the two branches are different.
Yes, that's exactly right. So I've got one branch which is root 16 minus x squared. The other branch, which is the bottom half of the circle, is negative root 16 minus x squared. That may not be clear from my bad handwriting here. Oh, wow. That's interesting. It's like the vector logo. Okay. So we have the positive root, we have the negative root, and the positive root defines that top half, and the negative root defines the bottom half. And so you can see that each one is legitimately a function of x.
So the two branches are both functions, they're different functions that both satisfy the...
Yes, exactly. That's right.
And neither of them cover negative 4 and 4?
Both of them actually cover negative 4 and 4, interestingly. Okay. And that can happen. And right at the boundaries, we don't fuss too much. about what's happening right at the boundary points in this box. In the bigger picture, we would say that, well, we would say that the derivative is infinite. The function is not differentiable at any other points of the branch. So in differential equation theory, we actually require that our branches be defined on, or at least one approach to differential equations is to define our branches only on open intervals. So that kind of thing can't happen. It's also possible to do differential equations on compact sets, in which case you embed your compact sets in larger open intervals. Okay, so coming back to our story, which is much easier, less thorny question, we take a derivative with respect to x on both sides, and we just walk through a term at a time differentiating, paying attention to the variable, with differentiating with respect to x. And so here we go. The derivative of x with respect to, the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 2y times, we can either write it as dy dx or y prime. Actually, since the problem asked us to find dy dx as a matter of style, wow, I will write dy dx right here. Smartboard, you're fired. Now on the left-hand side, and this is where students often make mistakes, please observe that the rate of change of 16 is 0. Always an old.
Wrong answer.
Well, yes, 16 is a very common wrong answer. People just copy the constant down and don't think about rates of change. And so when we solve for dy dx algebraically, what we get is this expression right here, negative x over y. This is a really interesting expression because what this does is to define the slope of the tangent line in terms of the entire point x and y, not just x. Now, why does that make sense? It makes sense because we have 2 branches on our curve.
Why is it not positive? It's negative x over negative 2.
It's because I added an extra negative sign and didn't belong. There you go. Yeah, subtract 2x from both sides, divide both sides by 2y. Good catch. All right, so we have a really interesting thing going on here because the slope of the tangent line depends upon the values of both x and y. In other words, on our branch. If I am looking at the top branch, and I'm at the point, let's see here, what's a good point for this curve? How about 1, root 15? That works. X squared plus y squared is equal to 16. Then my slope will be negative 1 over root 15. Based upon plugging in the values of x and y. But if I'm down here on the bottom branch, so that my x is 1 and my y is negative 1 over root 15, look at that. Yeah, I get a positive slope, which is the opposite of x over y. Interesting. Same x value, 2 different slopes because 2 different branches. Yeah. Makes a whole lot of sense. Now, with this dy dx, I can answer all sorts of interesting questions, such as, where are there points of horizontal tangency?
On y was x.
But now, when I ask this question is going to require more careful attention than when we had explicitly defined y equals f of x. Yes, ma'am?
I don't know, both instead of 1 root 15.
I just picked a point on the curve, and since x squared plus y squared is 16, I picked x equals 1 and solved for y in my head.
So do all implicitly defined functions, do they all have branches?
The implicitly defined function that we had as our second example right here, if you write this explicitly by solving for y, you get y equals x squared plus 2x plus 3, which has one single branch. So yes, they all have branches, but it might just be one branch. Yeah. So you can think of explicitly defined functions as a subset of the implicitly defined functions. Move y to the other side, and you now have an implicitly defined function. Did I just say move? I did. This one also, by the way, has a single branch. If I solve for y, I get y is the cube root of x cubed plus x. Okay, good questions. Where are the points of horizontal tangency? So I'm going to find those points of horizontal tangency, of course, by setting dy dx equal to 0. And when I do, I find out that this gives me
X?
yes, it gives me x equals 0. So I'm done, right? Wrong?
No, y does not.
Ah. I need points, and my points have a y coordinate. So I need to come back and identify all of the points that we're talking about by substituting into the original equation here. Let's do that. 0 squared plus y squared equals 16. Avoid the new mistake. And get two solutions, not one. Y equals 0 or y equals negative 4. And so this now gives me the two answers to my question, 0, 4, and 0, negative 4 as the 2 points of horizontal
Oh,
tangents.
we can just,
And there they are.
you guys have what are points?
Yes, that's right.
If I didn't say that, I'll just say it when X equals.
It will, always. And the reason it has to is that sometimes you can end up with phantom points. You can get x values that do not correspond to actual points on the curve. And I'll show you an example of that probably tomorrow. We do this, yes.
I forgot that.
Yeah, tomorrow. Yeah, or if we have time today.
And yesterday? No.
No, but I haven't. So I can take it.
Okay.
Yep. Now we can ask a similar question. Where are the points of vertical tangency?
And y equals, when it's infinite, it's infinite.
Yes. What we're really trying to do is to find the places where dy dx is infinite. But that's going to occur when y is equal to 0. But we can't be done there. We have to solve for the points. That's right. But we know how this is going to go. We're going to get two solutions. So our
3 and then go to 8.
Okay. And there it is.
Okay. Questions?
No. We have plenty to do. I want to say a little bit more about this. Maybe what I'll do is this. Let's do this. Let's have an elliptic curve. Y squared equals x cubed plus x plus 1. You can see that this is an implicit function. All that I have to do is to subtract y squared from both sides, and I get something equals 0. Now the first thing I want to observe is that your calculator is going to struggle to grasp this. Rightfully so, because you literally would have to go through an entire plane, coordinate plane, to see where your solutions are. However, there is some software that can do it, and I'd like to introduce you to Wolfram Alpha.
Is that an active?
I think they do have an app.
Yes, you recommended to us last year.
Well, the one I'm familiar with.
And the app costs like $3.99.
Oh, does it?
All too much.
Okay. Is it x or x squared in my example?
It goes X.
Or just x?
Yeah.
Okay. And now when we graph this guy, lo and behold, it gives us a very cute graph, which is an example of what we call an elliptic curve. I missed something. What's
I don't think I need a translation to figure out.
Okay. All right. Well, in any event, this is an example of an elliptic curve. And observe that it has top branch and bottom branch. And it's not surprising that the top one is y equals root x cubed plus x plus 1. Bottom one is y equals negative root x cubed plus x plus 1. And now what we're interested in doing is finding points of vertical tangency or horizontal tangency. So let's actually do that. And so we need a dy dx, and so we'll take it in either form here. So, and so on the left-hand side, on the right-hand side, like so. And this gives us okay. And now if we want horizontal or vertical tangency, I see where I messed up. I wanted subtraction to begin with. That's okay. We'll come back and do it again tomorrow. You can see that I'm not going to get any zeros here for this guy. We'll come back and do it again tomorrow. With a different example. If I set this equal to 0, what I get are no solutions. Because 3x squared plus 1 cannot be 0. If I set this equal to infinity, then that's going to give us y is equal to 0. Well, if y is equal to 0, then that means that my zeros are going to be the solutions to x cubed plus x plus 1 is equal to 0. And for that, I'm going to need to use a solver. Yeah.
The numerator can't be 0 because you can't take the square root of the negative.
Exactly. We would end up with two imaginary solutions here.
So is I.
Yeah.
But I think that works.
But this does. That's right. So we'll end up with one point of vertical tangency, and that point is going to be at the solution to this equation, which I think from your grapher is like negative 0.6711, something like that. Let's ask Wolfram alpha. Solve. Thinks for a second. It actually gives us an analytic solution, which is ridiculous. Where's our decimal plot? Approximate forms. Here we go. Negative 0.6823. And so this is the kind of analysis that we frequently do here. I want to finish this off. We've got a code red drill here pretty soon. I want to finish this off by extending our power rule. We use deduction to prove that this is the case when n is an integer. We use deduction to prove it for positive integers. We use quotient rule to prove it for negative integers, and the case n equals 0 was trivial. So we've got the power rule for all integers. What we'd like to do is to extend this to consider now all rational exponents, like so. And I claim that this is in fact also the same power rule. If the derivative of x to the m over n is simply bring down the power m over n times, subtract 1 from the power x to the m over n minus 1. And the proof is going to be pretty straightforward. Let's let y equal x to the m over n, where m and n are integers. And the problem with this is that I don't have a power rule for this. I only have a power rule for integers. So I have to say to myself, self, how could I get integer exponents for everything? How could I get everything inside can have only integer exponents? Yes, we did.
You put a you just put I.
Yeah, that would be clever. But I want integer exponents for everything. For example, how could I write this in terms of integer exponents only? Yes. Okay, keep going with that thought. That still doesn't give me an integer exponent. In what way? Yeah.
You would cube both sides, so y
Oh.
cubed equals x squared.
Look at that. That's exactly right. So coming back over to here, I would get integer exponents everywhere by doing what?
Y to the n equals x to the n.
Yes. This is a big idea in math. If I've got a tool that works for a particular case, then I can take a new case and try to get it into the form of the case that I've got the tool for. And now I can take a derivative with respect to x on both sides.
Attention. This is a lockdown.
All right, so the derivative process is pretty straightforward. And we get dy dx is equal to this thing. Now, at first it looks wrong, because what we were looking for was m over n times x to the m over n minus 1. However, all is not lost, because observe that we have the coefficient we want. But we have this expression in terms of y. That's begging for a substitution. Let's do that. It's going to give us m over n times x to the n minus 1 over y to the n minus 1. And that is going to give us x to the n minus 1 over, now multiply the exponents, and what do you get? X to the m times x to the negative n over n. Well, this is pretty straightforward. X to the m is canceled, taking a factor of x to the minus 1 behind, and 1 over x to the negative m over n is the same as x to the m over n. So that I get x to the m over n minus 1, which is exactly as advertised. That's it.